A quiet office environment shatters when thick, dark ink suddenly bleeds through the seams of a pristine white printer casing. Once that leak begins, you have exactly 5 minutes before thousands of dollars of internal hardware becomes permanent e-waste. These machines are volatile chemical reservoirs suspended directly over sensitive electronics. Every inkjet printer operates in a constant, hidden struggle against gravity. Losing that physical contest for a single second guarantees a fatal machine failure. To understand why a reliable machine suddenly self-destructs, we have to look past the digital specifications and examine the microscopic physical forces trying to keep that liquid contained. The true battleground is located deep inside the printhead, at the microscopic scale of the individual ink nozzles. This diagram illustrates the core engineering principle keeping the ink inside: negative pressure. Negative pressure is an internal vacuum force created within the cartridge that actively pulls the ink upward, precisely matching the downward pull of gravity. This precise vacuum seal holds the fluid at the very edge of the opening, forming a stable meniscus curve. A meniscus is the outward bulge of the liquid, where surface tension acts like an elastic skin, preventing the fluid from dripping. Maintaining this exact tension allows the system to forcefully eject a single microdroplet on command and immediately snap the remaining liquid back into place without a continuous flow. As long as the mathematical relationship between the internal vacuum and the fluid's weight holds, the delicate circuitry sitting directly beneath the reservoir remains completely safe. That delicate equation fractures when exposed to common environmental factors, starting with standard summer heat inside a home or office. As ambient temperatures rise, the thermodynamic properties of the ink change. The heat lowers the ink's viscosity, its natural thickness and resistance to flow, turning a dense fluid into a dangerously thin liquid. Time acts as a second compounding threat. As ink ages past its expiration date, its chemical composition degrades, weakening the molecular bonds that hold the fluid together. The combined effects of heat and chemical degradation alter the physical weight and behavior of the liquid inside the cartridge. The factory-calibrated negative pressure is now trying to hold back a different fluid than it was designed for. The failure occurs the moment the thinned, degraded ink can no longer sustain its surface tension at the exit point of the nozzle. Looking at the nozzle diagram again, we see the catastrophic tipping point. The internal vacuum effectiveness drops by a fraction of a percent, and the upward pull can no longer match the constant, heavy downward arrows of gravity. The meniscus ruptures completely. Gravity seizes control of the fluid, pulling the unstable ink in a continuous, unstoppable freefall straight through the channel. This uncontained liquid instantly floods the internal casing, seeking the lowest point and coating the microscopic electronic pathways of the printhead. A microscopic failure in fluid dynamics translates instantly into fatal, macro-level hardware destruction. Once the vacuum fails and the conductive ink shorts out the motherboards, the machine becomes irrecoverable e-waste. The inkjet printer is a highly sensitive analog fluid management system. Because it relies on physical properties rather than digital code, it requires strict environmental equilibrium. Maintaining consistent room temperature and careful physical placement are strictly required to keep the internal vacuum intact. Preventing this collapse requires active maintenance, utilizing climate control, discarding expired ink cartridges before their chemical makeup degrades, and running regular diagnostic prints to keep the nozzles clear. Ignoring the delicate physical forces at work inside this plastic box guarantees that your next print job will be the one that destroys the machine forever.